Hi class, in this lecture here I want to move into section 3.2, and this is talking about logarithmic functions. And you might have remembered what a logarithmic function is from your pre-calculus course, so I'm just going to do like a real brief introduction to what a log function is, how to write its equivalent form as an exponential function or an exponential expression, graph a very simple one, and then I'm going to get into the calculus of logarithmic functions. Okay, so what is a logarithmic function? So a logarithm is defined as the following. So log, and then with the subscripted a of x is equal to y. So this right here, this a, this is the base. Okay, so this is log base a of x is equal to y. And what it means is its equivalent statement is a raised to the y power is equal to x. And this is for a greater than 0 and a can't equal to 1. So if it helps to see it, right? So like this is the exponential expression. The log gives us the exponent. The base of the exponential expression is the base of the log. Okay, so the number log a of x is the power y to which we raise a to get x. Okay, so as I said, the number a is called the logarithmic base, and we read this as the logarithm base a of x. So log base a of x is what I will say. Okay, and I'm going to go through this pretty quickly. Obviously this should be a review for many of you, hopefully all of you. Okay, so the first one I want to do is just what does the graph of a log look like? So let's take one of the easiest ones. So let's graph the expression y is equal to log base 2 of x. So this equation here, let's graph this. Okay, so first we're going to write it in an exponential form. So we're just going to switch it around, right? And we're going to write it as 2 to the y is equal to x. Then what we will do is we will select some values of y to find the corresponding x, right? Because we can plug in values of y and get x. Next, all we're going to do is we're going to plot these points, but just still keep in mind, right? Like when you plot ordered pairs, the x always is the first coordinate. So you're just going to, normally you take x, plug it in the equation and get y. Here we're going to take y, plug it into the equation and get x. So what you're going to do here is you're going to select, and remember going back just real briefly here, right? These log functions here, okay, what you're going to notice when you do them is that this will, even when you write this equivalent expression here, the x value you can't plug in is negative. Like there's no way you can get a negative value for x, right? Like when you take 2 to the whatever power, there's no way it can be negative. All right, so going back, we're going to plug in values of y and get x. So I'm going to pick values of y, 0, 1, 2, 3, negative 1, negative 2. And when I plug them in, 2 raised to that power to get x, as I said here, you're going to see that x is never negative. And when you were to just plot these ordered pairs, 1, 0, 2, 1, 4, 2, 8, 3, so on, 1 half, negative 1, 1 fourth, negative 2, this is what the graph looks like. And you're going to notice that this graph has a vertical asymptote at the y-axis. And the reason this is if you remember, the exponential function had a horizontal asymptote at the x-axis. It turns out that these two functions, logs and exponentials, are just inverses of each other. So, if you think about there's a horizontal asymptote for the exponential, then there's going to be a vertical for the logarithmic. But this will always be what these graphs look like. Now you can do things like you can shift it to the left, to the right, up and down, things like that, but it's always going to still be this basic shape. Okay, so there's two common logs. So for any positive number x, if you have log of x, if there's no base here, okay, notice how the base is missing, it's just written as log. This is actually log base 10, and this is called the common log. But the one that we're going to deal with in this class, the one we'll work calculus with, is the one that looks like this. So for any positive number x, we have ln of x, okay? And this is log base e of x. So whenever you see ln, okay, this is referred to or called as the natural logarithm. Okay, it just means log base e. And, if you think about it, right, like in the previous lecture, we learned how to do calculus with e raised to whatever power. So now what we're going to do is we're going to focus calculus on the natural log. Okay. So here are just some properties of the natural log, and it's the same properties for all logarithmic functions. I'm not going to go through them all here. It should hopefully be a review for you. But, like if you have the natural log of m times n, that breaks up as addition. So log m plus natural log of n. Division breaks up as subtraction. You can bring an exponent down in front, and you can see the rest here. All right, you want to use these rules to help you find the derivatives of natural logs. What you'll notice is as you go to work these problems, you're going to get these really hard expressions, and they'll say, find the derivative of this. Well, it'd actually be easier to find the derivative if you broke up the log using these rules first. All right, and I have an example of this so you can see exactly what I mean later on. But all right, so I talk about what are the derivatives of natural logs. But before I do that, let me just do a quick review of how you would solve these equations. All right. So suppose you have e raised to the negative 0.4t is equal to 0.05. And to solve this, what you're going to use is you're going to use this rule P3 and P4 here. So you would take the natural log of each side. Well, so we're using this rule 3 here. You can bring the exponent down in front. So this becomes minus 0.04t times the natural log of e is equal to the natural log of 0.05. Well, look here. The natural log of e is just 1. So this is minus 0.04t is equal to the natural log of 0.05. Let's divide both sides now by minus 0.04. And you get t is equal to, you can just use your trusty calculator here. So it's the natural log, so you can see the natural log button here, of 0.05, close that parentheses, divided by minus 0.04, and it's roughly 74.89. I'll round it to 2 decimal places. Okay. Now let's get into the calculus here, okay? So for any positive number x, if I ask you to take the derivative of the natural log of x, it's very easy. It's literally just equal to 1 over x, okay? So whenever you see the natural log of x and you have to take the derivative, boom, it's just 1 over x. Let's do some examples. So let's differentiate here. So here, y, so I'm going to differentiate dy dx is equal to 5, and then when you come to the natural, differentiate the natural log, just 1 over x. So here dy dx is literally just 5 over x. Over here you're going to need to use the product rule to find this, right? So dy dx is equal to, take the derivative of 3x, you get 3x squared times the natural log of x, plus x cubed, and then you go to take the derivative of the natural log of x, it's just 1 over x, and then the derivative of 4x is plus 4. And then you can just clean this up, right? So it's 3x squared, natural log of x, plus x cubed, 1 over x, plus x squared, plus 4. Now here you're just going to use the quotient rule. So dy dx. Take the derivative of the numerator, 1 over x, times the denominator, minus the derivative of the denominator, x squared, times the numerator, natural log of x, all over x squared squared. So 1 over x times x is x, minus, and then I got 2x, natural log of x, all over x to the 4th. And then what you can also do here, if you see it, you can factor out another x, and you get 1 minus 2 the natural log of x over x cubed, because that x you factor out will cancel with the denominator there. And you'll want to fully reduce these problems when you come to them. Okay, so now let's talk about the chain rule as applied to the derivative of the natural log. All right, so all this is the derivative of the natural logarithm of a function. Okay, so it's something like the natural log of f of x, okay, where f of x is like 2x or x squared, something like that, is the derivative of the function divided by the function. Okay, so what you're going to do here, all right, you're going to take the derivative of whatever f of x is. Okay, so it's the derivative divided by whatever is originally in there. So, or if you can see it using the u, it's the natural log of u is equal to 1 over u times du dx. Okay, so I'll just use this notation. So if you have the natural log of some function, f of x, okay, something other than x is embedded in here. If I take the derivative with respect to x, this is just the derivative of whatever this inside function is divided by whatever the function is. All right, let's do some examples. All right, I've got actually 4 of them lined up here. So let's differentiate here. First, we'll start with this one. Y is equal to the natural log of 3x. All right, well, dy dx, remember, it's just the derivative of whatever's inside the natural log divided by whatever's there. So the derivative of 3x is 3 all over 3x. Well, this is still just 1 over x. And that works. Whenever there's a number in here, that's how this will always be. Okay? Another reason is you could actually break this up using your rules of exponents or your rules of logs. And this is just a constant. So when you go to take the derivative of this, it just goes away. All right, so y is equal to the natural log of x squared minus 5. So dy dx here. So remember, you take the derivative of the inside. Okay, so this is 2x all over x squared minus 5. You just leave whatever's there as is. Okay, let's try this one. This one looks a little bit tricky. So f of x is equal to the natural log of the natural log of x. Yikes. All right, so how do you handle this? Okay, so f prime of x. Well, what is my inside function, right? It's 1 over x, or excuse me, is natural log of x. So what is the derivative of the natural log of x? It's 1 over x divided by, and then whatever the inside of this natural log is. Well, the inside of this natural log is the natural log of x. So this, you just bring this down. So this ends up just being 1 over x times the natural log of x. Okay, so remember, this is my f of x inside here. So you take the derivative of f prime of x. Well, the derivative of this inside part is 1 over x divided by f of x, which is just the natural log of x. Okay, so this one, d. What you actually want to do here is you do not want to do like the quotient rule. Okay, you're going to make that really hard on yourself. So you could actually break this up as the natural log of x cubed plus 4 minus the natural log of x. And now all of a sudden it's super easy to take the derivative. So here, you take the derivative of this first. So this just becomes 3x squared over x cubed plus 4 minus, and then the derivative of the natural log of x is just 1 over x. So if you can, so this is my tip. So use your rules of logs here to break it up. Otherwise, if you try to do the quotient rule and stuff here, it's just not going to be fun, and I would not recommend it. So if you can, use your rules of logs to break it up. All right, class, I hope that helped.